for having to deal with the NBS stuff, now I'm going to draw up another multi-step synthesis here where we have a product which looks kind of crazy. But again, if we can name this product as what it really is, which is called a Diels-Alder adduct. And where does this come from? Well, this comes from a diene. And where does the diene come from? Allylic halide. A halogen that is on a carbon adjacent to a double bond. But these allylic halides actually come from alkenes. And the rest we should know from what we did earlier this evening, and that is that alkenes would go back to the haloalkane, which would then go back to the alkane. Haloalkane and alkane. And now for the reagents. Br2 and light. Then we have NaOH. This is where our NBS comes in. NBS, which is N-bromosuccinimide, brominates allylic to the double bond. Again, we put in NaOH to get our diene. And then lastly, what we got to do is we got to look at the portion of the molecule that is over here. This is going to dictate, because there's still a double bond there, that I actually had a triple bond here with the CO2 CH3. You get the idea, it's the same thing on both sides. But again, because there's a double bond here, this starts out as a triple. If it's a single bond, this would then be a double bond here. And remember one thing, whatever the orientation is around the double bond here is the way these two groups will stay oriented if I was reacting with alkene instead of the alkyne. Here's my diene. This compound right here is called the dienophile, because it's what we reacted diene with to give us our new compound over here. And the 5-membered ring was right here for the original compound. And in the blue is actually from the dienophile. The pink here would be the new bond formation that you had going on here. Now I want you to look at this reaction here and basically look at what it's asking. Draw a mechanism that supports the formation of the two products, and draw an energy diagram and write a short explanation why the percentage of the products changes at different temperatures. Remember to include comparison of kinetic versus thermodynamic control. You should be able to now do this by what was stated earlier in this review, okay? The last thing that we haven't talked about was electron donating groups on the diene and electron withdrawing groups on the dienophile affect the product in a Diels-Alder. D means donating, W means withdrawing. When you have a donating group at the 2 position here, it makes the 1 position, where my cursor is right now, a little bit negative. Now with the withdrawing group here, that makes this carbon up here a little bit positive. So the negative and the positive get close to one another and they link up, causing the withdrawing group and the donating group to be across from one another and not form any of the 1,3 product. As opposed to if the donating group is here at the 1 position, not the 2 position, then negative charge builds up at this 4 position here. Again, positive charge builds up where my cursor is right now on the dienophile, and therefore what we wind up is with a 1,2 product, and again, no 1,3.
So what we're going to look at is the fact that we've got this ring, and what's the first thing that's reacting here? BH3 and THF. But what's important for the mechanism is actually the BH3. We're going to have this bond come down and pick up the H as the boron comes over to this side. So the H and the B have actually added from the same side. So let's bring in our 2 reagents, hydroxide and H2O2. The hydroxide is going to hit this proton here and then come off, and then it's going to form HOO. And what's the charge on this O here? negative. And also we have water. So what we're going to do here is allow this here to come around and slam into the boron here. Now boron is in what group? 3, right? So if it's in group 3, how long do you think this thing wants to have 4 bonds? Not very long. Now what's attached to the boron now? OH. And the charge on the boron? Negative. So if you think about this, we've got a boron that's negatively charged. And somehow, we gotta get this thing to go back to being what? Just having 3 bonds. This bond here migrates over to the oxygen and releases the OH. So what does it look like now? What's bound to the ring now, the B or the O? It's bound to the O, which is also still bound to the boron. And the other thing that was up there was, freely floating is the OH minus. So that attacks here and kicks this out. Is there anything floating around that we can use? H2O, of course, right? Water. What's good about it is when we use it, we're going to regenerate the hydroxide. So if I allow this to come in, pull off the H, right? Got my final product with the hydroxide. That's the worst mechanism you're going to see in this chapter. Let's look at it again. Now, in that first step, when both groups go in from the same side, what do you call that? Syn addition. SYN. Syn addition means it comes in from the same side. That's why here I have them drawn on the same side. As opposed to what we're going to see in a minute with the addition of BR2, where they add from opposite sides. So we first have the syn addition, the BH, and the B. Then we have the reaction of hydroxide and peroxide to form O-, which attacks the boron. And then this thing that's happening down here, migration, where the bond between the carbon and the boron goes over to the oxygen, and this replaces hydroxide. Notice how it comes back and frees molecules, so in the end, when the alkoxide, the O-, hits the water, we regenerate OH and get our final product.
Our second reaction is catalytic hydrogenation. Again, what we see here is the 2 hydrogens add in a syn fashion, where the double bond swings down, picks up 1 hydrogen, where the bond between the 2 hydrogens adds to the other side of the double bond, forming the 2 H's on the same side. Here's the Br2 in water. This is called halohydrin formation. The only thing I want you to realize here is that the 2 groups should be on what? Opposite sides from one another. And the last 2 that I want to talk about in this review are the ozonolysis, where again this is a milder oxidizing condition so that we get an aldehyde. See, here's our aldehyde, and not like the hot permanganate, which gives you the acid.